All right, students, like normally, we just ran out of time in order to just get through the material, let alone showing you a few calculations. So, thought I'd make this little supplement. You can choose to watch it or not. But I'm hoping it'll be helpful for some of you to kind of see work through. So I picked some problems from each of our sections we talked about. Let's try number one. This goes all the way back to Hooke's law. This is the one that I said is kind of a review. And so maybe we did it kind of quickly, but hopefully it's not too complicated. Let's read this. It says, fish are hung on a spring scale to determine their mass. Most fishermen feel no obligation to truthfully report their mass. A, what is the force constant of a spring in such a scale if the spring stretches 8 centimeters for a 10 kilogram load? All right, so Hooke's law says that the magnitude of the force is some spring constant times the distance it has fallen. And so if you're just taking a spring and hooking, in this case, a 10 kilogram load, the force would be M and G, which then would be 10 kilograms times 9.8, which of course is 98 newtons. So there I would say is the left-hand side of the equation. Now the other side of the equation would be a constant and then divided by how far it stretches. And there we can either use the 8 centimeters or do the normal base units and convert it into a meter. So I think I will do that. And then that way, when I move the 0.08 meters to the other side, I will get an answer in newtons per meter. And so taking 98 and dividing it by 0.08, I get a spring constant of 1,225 newtons per meter, and I suppose 1,230 might be more appropriate given the three significant figures. All right, so there's A. We have a spring constant. It says, what is the mass of a fish that then stretches? 5.5. So maybe I'll start with force. And with a spring constant of 1,200 and I'll call it 25, why not? One extra significant figure, newtons per meter. And it stretches it, and I'll convert it into meters. It said 5.5 centimeters. So move the decimal 2. I will then take that number and 0.055. And so that is a force of 67.4 newtons. Now it actually says the mass, so this would be mg. So the mass needs to take that number and divide by g, 9.8. And so we're looking at something that's about 6.88 kilograms. And again, clearly below the 10 kilograms, since they said the 10 kilograms stretches at 8 centimeters, and this one stretched at something less than that. All right, and then says C, how far apart are each half a kilogram marker on this scale? So again, if it just kind of stretches and you got little markers so you can read them, you might do something like this. Again, starting with Hooke's law, the magnitude of the force would be kx. So a little change in x would correspond to a little change in the force. And so they're suggesting that our increment, our change, are a half a kilogram. And so this must be 4.9 newtons. And then, of course, multiplied by this 1,225 newtons per meter is then going to tell us the delta x, that is the physical spacing between each of these. So 4.9 divided by 1,225 comes out to be 0.004 meters for delta x. Maybe I'll change that to 4 millimeters. And so every 4 millimeters, we'll put a little mark saying, okay, this is a half kilogram, this is 1 kilogram, this is 1.5, this is 2, 2.5, and so forth and so on. Okay, so that's kind of the first one that comes to mind. And kind of debated if I should do that one, since that was the one that was review back to our conservation of energy, which I believe is chapter 7. All right, so let's try here number 7. Number 7. Oops, I need to. I went too far here. Here's number 7. It says, what is the period of a 60 hertz electrical power? Now, I picked this one, and now I wish I would have said something in lecture, not just here in the supplement. But when we did frequency, the definition was the number of cycles per second. Whereas the period was really the amount of time per one cycle. So the units for a period are pretty easy. It would be times or even minute, some kind of unit of time. So second, minute, hour, but the base unit would be a second. So we'd say how many seconds does it take? Now, the frequency is then the reciprocal, and that's why the units come out to be per second. Now, for clarifying it, we usually say the number of cycles per second. Okay. But in either case, this gives me a chance to point out that this is then a Hertz, abbreviated HZ. And that's really the only new unit. We did like wavelength, but that's a length, would be in meters. We did period, so that would be in time, so seconds. We did velocity, meters per second. So almost we did amplitude. Again, that's a distance, so it'd be in meters or centimeters. So really everything we did in this chapter was just putting together stuff we had learned earlier. I even said that if we put together Newton's second law, together with our kinematics, and together with our conservation of energy, we would work these things out. So this was more of a deductive reasoning, not new stuff. But there were one thing or a few things that were new, and this was really the one thing. So we've got a new unit to measure frequency. So the new quantity is frequency, and it's measured in hertz. So basically they say, what is the period? So they're looking for T, and they're giving you the frequency. And so the frequency is 60 hertz. And a 60 is a cycle per second. So when you take the 1 over 60 and flip the units, you get seconds per cycle. And cycle is just kind of clarifying. So we could drop it here and just say this is how many seconds. So it's 1/60th. Let's see. 1 over 10 would be 1 decimal place. And then 1 over 6 is 16666 repeating. All right. So there would be the period. All right. But not a real complicated one, but one that I thought could be useful because it would give you a chance to see the unit hertz. So that's why I picked it. All right, well, what's the next one I put on my list? 19. I'll put that on here for some reason, some hopefully helpful reason here. All right, so let me scan your book here and get to number 19. There's 18. So number 19 says, suppose a diving board with nobody on it bounces up and down in simple harmonic motion and has a frequency, so I'll say F, of 4 hertz. So up and down 4 times a second. You can say that the board has an effective mass of 10 kilograms. What is the frequency of a simple harmonic motion of a 75 kilogram diver who now stands on the board? Well, I think in all of this, they're trying to get you to think of a diving board as a spring. And I guess my picture has somebody on it. But even if somebody doesn't have on it, it would oscillate up and down. And if you put more mass on it, it still would oscillate up and down, but have a different period or different frequency. And so if you remember, our derivation here in class was that the period is 2 pi times m over k, or the frequency is 1 over 2 pi times the square root of k over m. But I think back here, when they give me kind of the empty diving board, and they give me the mass, and they give me the frequency, that gives me the tools to find k. And then once I have that, I can re-put it in with the new mass, with somebody standing on there, and answer their question, what is this new frequency? All right, so let's talk about without the person on it. And I'll use this. So the frequency is 4. I think that's what I wrote down. So it goes up and down in simple harmonic motion with a frequency of 4 hertz. And I'm just going to put 4 per second, okay, for the units. And then I've got the 1 over 2 pi. Then I've got this square root of k. And I've got a mass of, they say the diving board can be effectively 10 kilograms. All right, let's now solve this for k, and I'll do that by squaring. So this becomes a 16 and 1 over second squared. This becomes a 4 over pi squared, and this becomes a k over 10 kilograms. Now, looks like I'll move on to another page here. But this would be the 16. And I'm going to bring the 4 pi squared over. So 4 pi squared. And then I guess I still have the 1 over second squared for my units. And that would just be a k over a 10 kilograms. And maybe then I will get the k by itself. So the numbers are a 16, a 4 pi squared, and even a 10 when I bring this over. And then the units are a kilogram over a second squared. Now, I'll do the numbers first. So this is a 16 times a 4 times a pi squared times a 10. So I get an effective spring constant of 6,300, and I'll call it 17. Now, I'll also do this, that the units here might actually look a little wrong, but if you multiply the top and the bottom by a meter, this kilogram meter per second squared is a Newton, and then you're left with a meter on the bottom. And that's the units we're used to working with for the spring constant, newtons per meter. But notice right here that this, back here, the Newton has buried inside of it a meter, and they would cancel off. And so you could have written it in the past as kilogram over second squared. And you might call that the reduced units. You might even call that better. But I think it's reduced too much that you don't get to see the nicety that it's a force per distance. So I like the Newton per meter, even though, like I said, you might think that the meters should be canceled off. All right. Now, I'm not done with the problem, by the way. That's just the spring constant. So let me come back to the start of this. So now I can answer their question. It says, what is the frequency of this simple harmonic motion when you put a 75 kilogram diver on it? And so somebody walks out to perform a dive, and they jump up and down and let it bounce here. But this would be a frequency of 1 over 2 pi times the square root. And so here's the k value, 6,317 newtons per meter. And then we're going to divide by the mass. And the diver is 75, so the total would be the person and the board. So the board member was 10, so we're looking at 85 kilograms. So let me, whoops, I guess those units would be in here. Okay. So let me leave the numbers alone, but realize that inside of this square root is this Newton over a meter, which, as we said, would then reduce down to a kilogram over a second squared, because in the Newton, as we said back here, has a meter. And so if you get rid of that one with the one downstairs, you get kilogram over second squared. And then, of course, we're dividing it by the kilogram, so the kilogram goes away. And then when you take the square root, you just get 1 over second, which maybe we'll put cycles per second, or we'll put Hertz to simplify things. So, sure enough, the units do work out well. And so that's my unit analysis. Makes me feel like I'm confident and going somewhere. Let's put this number in here. So I got the spring constant, and I'm going to divide it by 85, and I'm going to take the square root. Then I'm going to divide it by both a 2 and a pi, and it looks like a rate of 1.17 Hertz. So about 1 1/3 Hertz. So board would go, in 1 second, the board's going to go, maybe I'll hold my hand this way. The board's going to go down, back up, and then back where it is. That's 1, and then go a little bit more, a third of a cycle. That'd just be passed down, maybe right there, because the other 2/3 would be this. So about a 1 1/3 cycles in 1 second. Okay. All right, good. So that one really got to the meat of this chapter in the oscillations, and used our units really well. All right. So what was that? 19. All right. So I've done 1, 7, 19. All right. Let's try number 22. And 22. What does it say? It says, what is the length of a pendulum that has a period of a half a second? Well, if you kind of remember our little derivation for the pendulum here, we basically argued that the K over M in the equation for Newton's second law, when we analyzed a mass on a spring, turned out to be the equivalent of an L over G as we analyzed the movement of a mass. So if we took all of our equations, and so for the spring, we had for the frequency this. Did I might have said this backwards. Yeah, this must be M over K. Okay. And then, oh, good. And that would make more sense, because all I really did here was take the 2 pi and replace the square root of M over K with L over G. And, of course, if we were being asked to find the frequency, I don't think that's the case in this problem, we would just take the reciprocal. Let me come back to the question. What does it say? The length of a pendulum that has a period. So let's use the one with a period. So we have here a half a second for the period, and then we have the 2 pi, and we're trying to solve for L, remembering G is 9.8 meters per second squared, and I guess they don't explicitly say we're on planet Earth, but I'm going to take it to be planet Earth unless they say otherwise. Okay, so again, working this out, maybe I will take this 0.5 here and divide it by a 2 and divide it by a pi. And so this would be 0.0796. And I guess the units would be seconds. Once I move the 2 pi over here, so we got square root of L, 9.8 meters per per second squared. Then, why don't I square everything? So in my calculator, I'll hit square. So 0.00633, and then it'll be seconds squared, equals L over 9.8 meters per second squared. And then finally, and I won't quite go to another page, but if I bring this on over, the numbers I just multiply, so times 9.8. So that would be a 0.062. And my, well, maybe I'll go 2-1 for 3 significant figures. Okay. And then the seconds would cancel off, and that would be meters. So it looks like in centimeters, it would be 6.21 centimeters or 62.1 millimeters. But maybe this is best, just right there. 0.0621 meters. And so again, another problem. It's kind of the heart of the chapter. It's part of the oscillations, and then this is the oscillations of a pendulum. All right. I guess we're about halfway done here. All right, let's try number 36 here. And I'm not sure what section this is or what the problem is, but I wrote it down for some reason here. Looks like it's kind of a good educational one in terms of engineering, if you will, because it's talking here about a building here. But it says, near the top of the Citigroup Center building in New York City, there's an object that has a mass, and I'm going to write this down, huge mass, 4 times 10 to the 5 kilograms. And it's on springs that have an adjustable force constant. Its function is to dampen wind-driven oscillations of the building by oscillating at the same frequency as the building is being driven. The driving force is transferred then to the object. In short, they're trying to say the engineers have this big building. We'll just kind of make a tall rectangular building. I don't know exactly what the Citigroup building looks like. But the problem with tall buildings is they get impacted with the wind, and the wind doesn't have to be traveling very fast, but it actually turns out to be a lot of force when the building is tall and wide. And so pulsations or turbulence can happen and can then be driving the building, and then the building can be shaken, okay? And one way then to stop the building from shaking is to have some kind of process where the energy doesn't actually shake the building, but shake some kind of real heavy mass up at top. And so that's really the design. The wind hits the building begins to shake, but the energy gets transferred from the building to the weight that's inside, and so the weight inside goes back and forth. But the building itself doesn't. And people in the building appreciate that a lot more. And so that's the logic behind this design here. This says, A, what is the frequency at which... Oh, sorry, that's the one above it, at 35. Okay. Hang springs that have adjustable spring constant. Its function is to dampen the wind-driven oscillations of the building by oscillating at the same frequency that the building is being driven at. The driving force then is transferred to this object, which oscillates instead of the entire building. Okay, so I guess that's what I was saying. So here is finally the question A. What effective force constant should the springs have to make the object oscillate with a period of 2 seconds. So the period, which is 2 pi times the square root of m over k, is going to say what spring constant shall we have. And so maybe on that given day, that given storm, the winds come in and make turbulence, and so it makes these little eddies that spin and then spin and then spin. And what they're saying is those effective eddy ones are changing at some rate. And it says here 2 seconds. So the building is eventually getting driven by 2 seconds. And what we would like to have is the spring constant to be adjustable so that the mass would love to shake at 2 seconds. And so thereby shaking the mass and not the building. And of course, this mass is 4 times 10 to the 5 kilograms. And now we can solve for the spring constant. So let me go ahead and take the 2 and divide it by a 2 and divide it by a pi. And so this is 0.318. Okay. And I guess I'll put seconds. Now, if you square both sides, you're going to get this 4 times 10 to the 5 kilograms over a k. Moving the k to the other side, leaving the mass alone, but leaving the period over here. We're going to get those same units we just talked about, which is a kilogram over a second squared, which is the same as a Newton per meter. And so now I'll take that mass, 4 times 10 to the 5, and divide it by that last answer squared. And I get, 3.95 times 10 to the 1, 2, 3, 4, 5, 6. So times 10 to the 6th newtons per meter. Yeah. Now, I believe there was a part B to this. What energy is stored in the spring if the oscillation is got a displacement or an amplitude of 2 meters from equilibrium? So if you remember our idea of energy in a spring going back and forth, at any position, some of the energy would be this, elastic energy, and some would be kinetic. But since energy is conserved, this has to be the same everywhere. And so if it goes all the way to its maximum left or its maximum right, then the kinetic energy is 0. And the x position is its maximum, its amplitude. Okay? And so that's the total energy. And so that's what I'm going to take advantage of here and use this spring constant. And then this is its amplitude of 2 meters. And as you can see, this is a big number because 2 squared is a 4, and half of that's 2. So if I just take this last number and double it, we're looking at 7.90 times 10 to the 1, 2, 3, 4, 5, 6. And that would be joules. And it's probably worth noting that it would be a Newton, and then this meter would cancel with one of these, and then be left 1 Newton, or 1 meter left over, so it would be Newton times a meter, which is a joule. So, not a surprise also, with such a large spring constant and a pretty good displacement. I mean, this thing's sitting on the top floor going back and forth by 2 meters. It's going to be a lot of energy there. it's over 1 million. It's getting close to 10 million joules of energy. So quite a bit. All right, so there's our oscillations. Next one I was thinking about for some reason. Let's look at number 53. Actually, that sounds advanced enough that I think now we're getting into the second half of the chapter that has to do with waves. So 53 says, what is the wavelength of an earthquake that shakes you at a frequency, so 10 hertz, and gets to another city that is 84.0 kilometers away in 12 seconds? Well, I don't know if you kind of caught that, but they indirectly gave us the speed at which these waves travel. So these are earthquake waves. This is a shaking of the ground. Remember, this chapter is all about waves in general. And I don't think I threw out earthquake waves. I talked about sound waves and light waves and water waves and waves on that little rod machine. But I don't think I said anything about the shaking of the earth, which would be earthquake waves. Although, as you'll see in the next chapter, really we could call those sound waves that are in the earth. But in either case, let me put the distance at 84, and notice it says kilometers. So I'm going to change that to 84,000 meters in 12 seconds. So this gives me the speed. And so we're looking at, I guess we didn't need a calculator for that. 12 times 7 is 84. Okay. But, which means 84 divided by 12 is 7, and then another 1,000. So this is the speed, which is about 7 kilometers per second. All right, so taking that to be the speed of our earthquake waves, this is really boiling down to be this, saying that there's a mathematical connection between wavelength, frequency, and velocity. The other one we had was, wavelength over period. But we're not going to need that one for this equation, because I would say that we know the frequency. They said the frequency was 10, so here's our shaking back and forth 10 times a second. And we just found its velocity. And of course, there's the question, the third one, what is the wavelength? So let me write wavelength as velocity divided by frequency. So we've got a very high velocity. Not going to outrun earthquake waves or even outdrive them if they're coming. You can't get in your car and take off. I guess you couldn't even get in a plane and get away from them, but if you're in the plane, you're off the ground, so it doesn't matter. But this is the speed, 7,000 meters per second, and a frequency of 10 hertz. And since the numbers are easy, I'll just go 700. 700 what? Well, remember a hertz is a cycle per second. So I'll just cross out hertz and replace it with 1/2. But see, at the top I have a 1/2, and the bottom I have a 1/2. So what I'll be left with is meters, as I should be, because this, again, would be a length. So it should be left in meters. And so I'd say the wavelength is 700 meters. Which is probably pretty good because, like I said, if I were to draw this, and here is the wave, fortunately, a house is much, much smaller than 700 meters. I mean, it might be as much as 10 meters at most, but if this then is the house, fortunately, it's small to the wavelength, and so the house, as the wave travels by, the house seems to go up and down, sort of like that seagull did in our water waves in the lecture. But what we don't have, if we had a more complex situation for an object that is, I guess from crest to trough would be half this. So if we had something that was 350 meters long, it would do this, and then the next wave would do that. There'd be a lot of twisty motion as it is going up and down. And that can be rough on a building. course, this can be pretty rough too, up and down. But fortunately, the up and down, the house is built for that. It's built for a heavy roof and compacting down. And so these long wavelengths are more of your survivable earthquakes. It's when you look at wavelengths that are in the neighborhood of the size of the building, and the whole building's going up and down and twisting. It can get pretty bad. And I should say that's for transverse waves. Earthquakes also have longitudinal waves, and so it shakes the house left and right. And that is hard on a house because as the ground shakes back and forth, it's built on these 2x4s that are really good at in this direction, but they aren't giving you a whole lot of support side to side. And so the base goes out and the roof is so heavy it stays there. And so it goes like that. And then the roof moves over right as the earthquake goes the other way. And if those match, boy, it's just really hard on a house. So it's the longitudinal waves or the waves of short wavelength that tends to be the problems in an earthquake, not the ones that I've drawn here, which have a long wavelength, and also it is a transverse wave. Okay, but I'll move on. Kind of a fun discussion on designing for an earthquake there. But this is not quite what we're after. All right, so let's look at another one here. Second to last here, number 58. 58 says, the middle C hammer on a piano hits 2 strings and produces a beat of 1.50 hertz. Now, this might be a good discussion. I probably shouldn't get too much into engineering again, but I just can't help it. That's what I normally teach, and I think that'll, I hope, pique your curiosity. Of course, I always got to remember for this class, it's not my normal class, but you guys always like stuff related to the life science. But a piano is designed, maybe I'll start with a single string. So inside of the piano is a string, and when you hit the keys, a little hammer comes up, and a felt-covered hammer, and it hits the string, setting it into an oscillation. And I'll just do what we call the lowest oscillation one, when we talked about our wavelengths being quantized and our frequencies being quantized. But this would set it into motion. Of course, you might also get that motion, even both of those at the same time. But as we set it here into motion, its vibration will then, I was going to say hit the air molecules to make sound, but really it's the vibration of this string that makes the wood in the piano then vibrate. And then the wood in the piano hits the air molecules, which then is what we hear, is the waves in the sound. So we've got to make our waves on our string first, which makes the waves in we call this the sound box, the wood. So a violin, or a guitar has its little sound box. So you play the guitar, and as you play the guitar, you then, of course, shake the little sound box, and then the sound box shakes the air molecules. Okay, so that's what's going on here. Now, in a piano, especially for your high notes, if you hit a single string, that single string just doesn't have enough mass and enough motion, so they double them up. So to make them sound better, you put 2 strings. And one hammer, you'd make the hammer wide enough that when it goes up, it strikes both of them. Now, here is where you can run into troubles with a cheapy piano, because if the tension changes, and it will. I mean, you can tune this to have a certain tension so that when you hit it, they both vibrate at the same rate. But after a week or two, one string will stretch more than the other. They'll both stretch. So if you don't get your piano tuned every week, and who does, but it's going to be slightly out of tune. And so unless you're a professional, you don't check it every day. A guitar you probably do, because you can just sit there and tune it yourself. But especially if you own a guitar, you'll know that you just got to adjust the tension on it. It just gets off a little bit. The little string stretches a little bit. But two strings is really problematic, because then if you hit it, they're going to be at slightly different frequencies, and you're going to hear what we called the beat. And so if you remember from the lecture, if you had two different waves, in this case two sound waves, because two different strings that are a slightly different frequency, you're going to get that wah, wah, wah. And that was easy to hear for you in-person people. You guys in the video lecture, I wonder how well it stood out. I should listen to the video. But I know that my lapel mic has an auto gain to it. So I'm kind of thinking that the electronics in the lapel mic kind of adjusted the amplitude. So you couldn't really hear the loud, soft, loud, soft, loud, soft. But it's also not exactly a perfect equalizer, because you do want a microphone that reflects people's voice, the intensity of their voice, the loudness, the softness. And so auto gains, you lose a little bit of that, but it's not that significant. But if you only have one little sound in there, the electronics actually loses it quite a bit. So you might not have heard the beats very well in the video lecture. But my cameraman was telling me he could hear it. So I know you must have been able to hear it a little bit, maybe not as dramatically as we in class heard it. Anyways, one more thing we better do this problem is then often your better piano, understanding this, will actually take the string and put it around a pulley and back. And that way you have your two strings, but as one tension changes, it'll roll along the pulley and keep the tension the same. So at least you won't get the beats as you play that note. And so you go ding, and it's like, oh, that sounds terrible. And so you'll put it around a pulley. So there's your hammer. So your hammer hits both of them. They're always under the same tension. Now, they still might become untuned just because it stretches. It's just the nature of the material. Although, if you're going to build something a little more complicated, you probably get a little better string that has a little more rigidness to it and doesn't keep stretching. But they all do. And so you always got to come back and do it. But at least you get, like I said, get rid of the beats. But the beat is the frequency difference between them. All right, so let's go back to the problem finally. The problem says that the middle C hammer on a piano hits two strings, producing a beat of 1.5 hertz. One of the strings is tuned to 260 with 20 hertz. What frequencies could the other one be? So in other words, the other one here, since it's absolute value, meaning this second one can be either 1.5 above this or 1.5 below it. So F2 has two options. We can have 261.5 hertz, so that would be frequency number 2 is a little bit above. It's 1.5 above this one. But we could also be 1.5 below. So 258.5. Either of these two frequencies would produce a beat. And so that's a beat of 1.5. And so there's our beat frequency. Okay. And one last one, and then we will call our supplement good. There's probably even more we could and should do, but maybe we'll just kind of address those as we do the video solutions. But the last one I put on my list is this 56, and I'm glad 67, and I'm really glad I did, because one thing that I didn't get a chance to do for our waves was to say that as they carry energy with them, that energy can be spread out over some area. So like if these are sound waves, maybe I'll have a little speaker here that produces the sound waves. And because of the principle of conservation of energy, I would say, okay, the sound waves have a certain amount of energy here, but that energy gets spread out over a bigger area as they travel. So what is referred to as its intensity. That is the energy per area drops down. That's why if somebody was standing here kind of close to the speaker versus standing here kind of far to the speaker, since you're not interested in all the energy, you're only interested in the small amount that goes in your ear. And so you're interested in the amount of energy per area. So even though the wave, as it spreads out, has the same total amount of energy, it's spread out over a bigger area. And it's the intensity that your body would call the volume of that wave. You would be saying, hey, it's less intense here than here. But you wouldn't say there's less energy in the wave. You would just say it's less intense. There's less energy per area, but it's spread out over a bigger area. So in other words, the total energy would then be a combination of the intensity times the area. And so it kind of depends, again, what you're after in both engineering and in biology. In biology, I guess it's really, you're probably just more interested in intensity because you want to know how much energy enters the living organisms, and I'll say humans' ear, and that's kind of a fixed area, regardless of how much it's spread out. Now, as an engineer, you're probably interested in this total energy. This total energy does need to get absorbed. This total energy does travel along. This total energy has to be produced by the speaker. And so there's a lot of reasons just to be interested in the total amount of energy. Okay. You might even say the rates of energy. Oh, it is the rate of energy. My bad. The intensity is the rate of energy per area. So it's power per area. And so we'd call this power. So let me say it again. As an engineer, you might be interested in the total, so the total power being produced. Not really being concerned about its concentration. That is, how much power per area does it have. But on the other hand, if that sound is going to go into, say, a microphone, a fixed area microphone, and you want that energy that comes in to be able to be enough energy to kind of start the whole electronics process. And so we'll talk about how microphones are built next semester. We get into Faraday's law. But this right here then would mean you're probably more interested in the intensity of it, not the total power. So generating it, you're probably interested in total power. But listening to it, either by the ear or by a microphone, you probably want to know the intensity. Anyways, I picked this because here's what it has. It has a discussion about intensity. And my example was with sound waves, but this happens to be with light waves. It says energy from the sun arrives at the top of the Earth's atmosphere at an intensity equaling 1.30 kilowatts per square meter. How long does it take for 1.80 times 10 to the ninth joules to arrive in an area that's 1 square meter? All right, so let me use power, which I will call the intensity times the area. And so the intensity of the upper atmosphere is 1.3 thousand watts per square meter. And of course, if I multiply by the area, and I think they gave me an easy one. Was it just one? Yeah, 1 square meter. So I would get 1.3 kilowatts of solar energy up at the, I believe they said this is up at the top of the Earth's atmosphere, because usually we like to say by the time the sunlight gets down to the surface, and so you're going to put in some solar panels, it's more like 1.0 kilowatts per each square meter. That's what this is, 1 square meter. Okay. And again, this is power, which is energy per time. So finally, we can say how much energy would it be? This would be the power multiplied by time. And so this power is the 1.3 kilowatts. And again, that's actually the area per square meter. And if we multiply it then by time, which I'll just put here for T unknown, because that's the question. How long does it take to get an energy that is equal to 1.80? And this, I guess, would be billion joules. Okay. So I'm going to take the 1.8 times 10 to the ninth and divide it by 1.3 times 10 to the third. Now notice 10 to the third because it's in kilowatts. And so we're looking at 1.38. And this is 6. 1, 2, 3, 4, 5, 6. So at this kind of low energy situation in 1 square meter, it would take 1.38 times 10 to the sixth. And we're, of course, solving everything in seconds. So this is, I guess, quite a bit of time. In fact, maybe I should convert it to something a little more useful. How about I divide by 60, that's the number of minutes, divide by 60, that's the number of hours, divide by 24, that's the number of days. Okay, so about 16 days. So how long would it take to, maybe you need this much energy. What was that total energy? I guess I didn't actually put it here. Oh, there it is. And so this is our energy we're looking for. So anyways, it's going to take a while, 16 days to build up. Okay, I'll call it good there. A bunch of good examples, more that we probably could and should do, but we'll address those on the homework as you have questions, and I'll do some video solutions. This is a good examples and a good supplement. It's still under an hour. Okay, bye.